Hello everyone. Uh, Today I would like to make another tutorial uh, about using SwiftComp GUI to compute effective properties of unidirectional fiber reinforced lamina. So usually we can consider there are lots of fibers inside a single ply lamina, and we would like to use a square peg model, which means we have a fiber at the center of this square shape, and then around this fiber is just the matrix. And we know the fiber properties and also the matrix properties. And we also know the fiber volume fraction. So based on this information, we want to get the effective properties of this lamina. And now we are going to use MSC solid model to help us to finish this work. Okay, let's get started. So this is the empty Patran database. As a command window, let me invoke SwiftComp first. Let's input as c.pcl. Okay, then you see SwiftComp menu is added as this menu bar. So first we go to geometry, and then let's see the object we need to choose surface, and the method is XYZ, and then we change a little bit about these parameters. This is not like required, but it would be make this problem become easier. So basically, when I change this origin coordinates list, I make sure the center of my model is at the 0, 0, 0 coordinate. So I click apply. And next, I go to object, and I want to draw a curve to represent the fiber. Okay, and then the method I choose is 2D circle. And here I need to input the radius of my circle, and let me see here. Okay, so we have previously compute the radius of the fiber so that the volume fraction can be 60%. So let me use this as the radius. Click apply. Okay, now we have the shape of our micromechanics model, but this just a curve on the surface. What we need is two separate surfaces. So next, I will use edit, and the object is surface, and the method is break. So the surface is this square, and the break curve is the circle. And click yes. Now I have two surfaces actually. Now next we need to define our material properties. So note we need for matrix properties, this is isotropic. So I give name matrix, input properties. So the properties should be let me see. Okay, here. Let me just close this one. Okay. 4769. Patran 4769. Then 4760. My bad. 0.37. Click OK and apply. Next, we want to define the properties of fiber. Okay, so fiber input properties, which would be two 76000 19500 19500, and the Poisson's ratio would be 0. Okay. Okay, now I have defined my material properties for fiber. Click OK, click Apply. Then basically you can check we have defined our matrix properties, which is isotropic material, and the fiber properties, which is 3D isotropic material. Then go to properties. Now we need to define our material properties to the element. Let's give it a name. First, the type here, we need to choose 2D solid. And I give a name as matrix, input the properties. We can choose the properties from this window. We choose matrix, click OK, and select the application region, which is surface 2. Click OK, apply. And then we do the same thing for the fiber. For the properties, we change this to fiber, click OK, select region, click here, OK, OK. Now we have defined the properties, assign the right material properties to the corresponding region. Now we go to element and just use some, basically define the state in each edge. But this part is customized. You can refine your mesh and choose whatever the mesh size you want. Go to mesh. So I would like to use triangular mesh, and the surface would be surface 2 and surface 3. It doesn't matter about the order. So click apply. Now I have my mesh. Not very good, but you can refine it later. And now we are ready to perform homogenization. Go to SwiftComp, homogenization, solid model, and we want to get the effective properties, and we don't involve any local coordinates, so we just keep this as default and click apply. Yes. And then you see the properties were automatically popped out. So yeah, that's all. Hope this video gives you some useful information. So enjoy it. Thank you. Okay, so now we have the effective properties using MSC solid model. What we have is the 3D material properties, and these 3D material properties can be used to define solid element to perform a structure analysis. So for 3D solid elements, the corresponding structure responses are the displacements, of course, and also the 3D strengths. So let me close this and open dehomogenization solid model. Let's see, we have performed structure analysis, and for a point, the structure responses, let's assume the strain is between 1 as 0.01 and give it a shear strength 0.005, for example, and I assume I don't consider the displacement, and I can click apply. You can see actually the displacement were automatically popped out, and we can see the counterplot of the results, like the displacement in the x direction. We can also check the stress and the strain. Let's say stress sigma 11. So we have the sigma 11, sigma 12, sigma 13. Let's say sigma 33. So you can see we have a very nice plot here. Epsilon 11, of course, that is a constant we just applied. Epsilon 22. So it's pretty easy. We can perform a dehomogenization to check the local displacement and the stress and the strain fields. So this is about the constitutive modeling using MSC solid model, which includes homogenization to get the effective properties and also the dehomogenization to get the local fields.